consistent output. The agenda, basically, I'm going to go over some of the input sources that obviously drive these technologies. How many are familiar with the STL file format? Okay. We'll go over a little bit on that, and you're hopefully going to laugh. You probably will. But nonetheless, we'll cover some material options, the manufacturing processes, as well as the impact of different applications and where you can really put these technologies. And I think that's a big area that a lot of people look at it and they have one application for it. But if you're going to get one of these pieces of equipment, or if you're going to utilize service providers, look at all the possibilities of where you can apply this, because there's a lot of benefit and it's a really powerful tool if used correctly. Then obviously there's production control points, and different people use different production systems, production methods, and it's defining who you're working with, what they're doing, and how that works with what you need. And then obviously working relationships, quality management systems, and some basics of it. So the STL file. The STL file was invented by Chuck Hall. Chuck Hall, the inventor of 3D systems, or stereolithography. And the reason he invented the STL file format is because he needed a simplified, dumbed-down file of a CAD model so that he could put it in and control where the laser would start and stop as it drew or traced the profile on a photopolymer. The issue with this is he basically just put triangles on it. Now, STL does not actually mean standard tessellation language or stereolithography file, it's just STL. And he was originally developing these on a 386, and we actually have an SLA1 that still has, we don't have the 386 in it, but we still have the 386 that it came with, but that was the computer processing power back when these came out. You know, now, I mean, how many of you have a smartphone? But this Apple iPad has more power than a lot of the current equipment that's producing parts these days. So it's kind of amazing how fast it's, but we still use this STL file format, as bad as it may be. Now, you may hear people say that your file's tessellated, or it's triangulated, or it's not tessellated enough. What they're trying to refer to is these triangles that you've got here. You can break any of these into more and more triangles. The more triangles you get, the closer representation you have to the actual part that you're trying to produce. So if they say that your file is tessellated, it means that it doesn't have enough triangles in it. The objective is to try and get that to the point where it matches what the machine can actually produce. Because you can make a tessellated file that's way over the size that any of these machines could produce in resolution. That said, if you look at this example here, you're not going to have any problem on your outer edges because they're nice and square. But when you get to your round surfaces or any of your circular or cylindrical features, those are going to be where you'll see some of the issues show up when it comes with the triangulation files. Now, getting into the material options, we know that we've got limits on the files. Okay, we can understand how to work with that, how to control and manage that. There's also issues when you translate from CAD files. I don't think there's any CAD system that translates exact everything without some loss of fidelity. Once you've gotten that defined, you need to pick out a material. And in stereolithography alone, which is the oldest technology, there's probably over 75 different materials available, of which 60 of those are probably really not used anymore. They're just older technology. That doesn't mean that they don't have viability. When you get into FDM, you've probably got a magnitude of about 10, 15 different materials to choose from, unless you start adding colors. You get into SLS, you've got a collection. You get into metals, and there's a whole nother selection of materials. So there's quite a variety of different ones to choose in the additive manufacturing cycle. Now, when you get out of that, obviously you go into the plastics and you can get into fabricated. There's tons you can choose there. For the metals, you've got the direct metal options, but you can also utilize any of these additive manufacturing processes to get patterns to take you to conventional manufacturing processes. The materials that are coming out of the direct metal systems are very good, but they're not necessarily exactly that which you're going to find on a design analysis or on a design title block. You may be dealing with the 17.4 stainless steel, but can you get the exact same properties as a precipitation hardened? There's a lot of battles going on with that because with these machines you can potentially get to a higher density than you typically can in an investment cast process. Now, does that mean you just go to a hipping process and try and get it to the same grade? Do some x-ray and see what you've got at the end? A lot of different options there, but there's still a lot of qualification that needs to be done to make those materials something that you can tell a designer, here you go, take it and work with it. So with that, obviously you can go into sand cast, rubber plaster cast, you can use patterns from a lot of these. Composites is an area that's really starting to grow up a lot. There are a few companies out there now that are actually manufacturing systems to create 3D printed composite parts. One of them in North Lake up here where they're actually printing the binder onto a sheet of Kevlar or composite, and there's another material I can't think of, but they're taking and stacking these then and then putting them into an oven. When it comes out, they're blasting away the area where the composite material does not have any of the binder. So now you end up with a 3D printed composite part. Strengths are really good. They're still trying to determine exactly the repeatability and everything in the Z direction because there's a lot of issues associated with it and it's new. So, not to mention the fact that their current envelope right now is just encroaching the 10 by 10 area. So scalability is still being defined as well. Silicone materials, there's a lot of silicone materials out there, liquid silicone rubber materials. A lot of these are very compatible with these processes to actually use and make tools off of these machines and produce silicone parts directly from them. This right here is an example of a tool that we made for a part that literally has severe undercuts. To produce that in a rapid prototyping process would be extremely difficult. Even the flexible materials that are available don't necessarily give you the same tear strength, chemical resistance, and heat deflection temperatures that you're going to find in a lot of the basic silicones. You can get silicone castable materials that have 1200 degrees Fahrenheit surface temperatures. So a lot of different options out there with materials, but not necessarily directly off the